vapor pressure obviously is affected by temperature. This comes out a very important equation. Clausius Clapeyron equation. What is that? Natural log E of P1 and P2 equals negative delta H, which is entropy generated during the absorption of the water, divided by R, which is a heat constant, bracket T1 minus T2. We're going to talk about this next week also. This comes out with an important table, an important conclusion, what it looks like. This is temperature, and this is vapor pressure. If the temperature at 20 degrees Celsius, what's the vapor pressure? 17.3 torr. If it's 40 degrees Celsius, 55 torr. If it is at 100 degrees Celsius, 760 torr. This is all the time people did the research. What is torr means? 1 torr equals 133.3 Pascal. That's a pressure measurements. And this is corresponding to the Clausius-Clapeyron equation, looks like here. Okay, so this goes a little bit complicated, but I will explain to you what's the vapor pressure. Now let's talk about the food products. What's the difference between a food product of a pure water? It's the ingredients. The ingredients in the food products is much more complicated. So what we have, obviously we have water. Okay, let's just draw two molecules. Then what we have? Salt. Is that right? We have sugar. These will be interacted with water. So, they still flee away. But the amount of flee away from the surface, we call it evaporation, will be dramatically decreased. Evaporation will be decreased dramatically. So what happened? This vapor pressure on the top will be dramatically less than the vapor pressure of pure water. Okay, I just write a VP right here. Therefore, we come out with this equation, we come out with water activity. Okay, what's the value of the water activity? If we gave you some example. A hot dog, let's say. 0.995 could be. We have a water activity meter at the lab. We will talk about how we measure it. How about the beef jerky? Little bit dry, 0.910. How about, let's say, a crack? A crack, that will be much drier. So this is usually 0.250. Okay, this is just give you some of the example. Now how about a raisin? This is relatively 0.510, some kind of ish like that. Okay, so this is the water activity we mentioned about that. We want to spend a little bit point to talk about this boiling temperature and boiling. So we want to spending a little bit of time talk about this here is boring water. Then we go to an important table right there. Okay, boring water. We mentioned about the vapor pressure of a pure water. If they equal atmosphere temperature pressure, then start to bubbling, start to have a boring happen. It is affected by elevation. So we know about it. If I draw the curve like this, it will be obviously like that. And we talk about 100, this is go, let's go 100. That should be go right here. Degrees Celsius, this is called the 70. This usually means it's at sea level. So this is elevation. So 100 degrees Celsius boiling temperature of a pure water is at sea level. This is actually never happened. Very few times will happen. Where are we right now? At West Virginia. We are in an Appalachian mountain area. So elevation slightly higher, about like 1,000 meters. So we tested in the lab before. The boiling temperature basically around 94 degrees Celsius. Now I know some of you used to be used to degree Fahrenheit. We'll get to that. Okay, when we talk about the equation. How about Rocky Mountain? Let's say Colorado, the place where I studied. In Fort Collins, Colorado, which is a Rocky Mountain area. We did the research also, a little bit tested. The elevation is roughly 1,500 meters. So that is usually 92 degrees Celsius, a little bit lower. Let's go to the highest mountain in the world, in Nepal and China. Everest, Himalaya mountain. If you're gonna cook an egg there, you put an egg into water. 72 degrees Celsius. It's gonna start to boil. This raised a question of food safety. If you go mountain area, not gonna be go that high, okay? If you go 3,000 meter mountain area, could be 80 degrees Celsius, 75 degrees Celsius, the water start to boiling. So if you prepare food, certainly does not make it safe. So that's raises the food safety question. It's an elevation. Second, it's a purity question. Let's give you a very simple example. If I dissolve, let's say, 75 grams of sodium chloride into 500 ml water. What do you think is the boiling temperature? Is that going to be increased or is it going to be decreased? Now, based on the vapor pressure concept here, certainly if you put the ingredients there, the vapor pressure will be decreased. So we need more energy to let it be equal the atmosphere temperature. So you can think about the boiling temperature will be slightly increased or more or less will be increased. This comes out with a formula which is delta T B, which is boiling equals I multiplied by K boiling multiplied by M. So we want to talk about that. We want to do a brief calculation. I is the number of chemical ions. So sodium chloride, how many chemical ions there? It's only two. Sodium and chloride. What is Kb? This is a heat constant of boiling water approximately equals 0.52 degrees Celsius kJ per mole. So what is going to be the M means? This is the molecular. This is the mole of chemicals. Okay, so what is that? This equals 75 grams divided by a molecular weight, a mass weight of sodium chloride. That's 23 add 35.5 of chloride equals 58.5. So we divided it by 58.5. And we need to also divide it by the amount of the water. We say 500 ml. That equals 0.5 liter. So this equals roughly, if you do the math, 2.67 degrees Celsius. And remember, we talk about this is delta TB. So what's the final temperature when we boiling a sodium chloride solution? It will be T equals 100 degrees Celsius of pure water at 2.67 equals 102.67 degrees Celsius. So roughly 2 to 3 degrees Celsius increased. Okay, so this is what we talk about is water activity. Now we want to mention the last one, but it is important. That is the correlation between moisture content and water activity. What is going to be looks like? We're going to draw a curve like this. Let's redraw it. This needs to be a little bit large. How to draw it beautiful? Let's do. That's a curve. X-axis, water activity. Now, by the way, water activity also could be related to equilibrium relative humidity. That equals 100% multiplied by water activity. Okay, E or H, equilibrium relative humidity. So water activity, what's the range? 0 to 1.000. Could be 4 digits. So we separate them into 3. This will be 0.25, 0.50, and 0.75. What is the y-axis? Moisture content. We should say equilibrium moisture content. What is going to be? Obviously on the top is 100%. Now we have like, let's just do 25, 50, and 75. So what's the relationship? Remember, I have a question for my students. I said, it is, what is water activity? She said it is the amount of the water, which is actually moisture content. The reason is, lots of the food products, the curve looks like this. It's very interesting. This is sorption isotherm. This is sorption isotherm, which means how the water activity and the moisture content, they connected with each other, the relationship. Based on this curve, we could differentiate food product into basically 3 different categories. What are those 3 different categories? The first one, is called monolayer. Basically is bound water. And the second one is additional layer, which is we call loosely bound water. And the last section is capillary water layer, basically free water. So we're talking about the free water and the bounded water, so what's the difference? Let's give some of the examples. What kind of the food? Majority of them are bounded water. Chips, cracks. Okay, we just said chips. What type of the food? Majority of the water is loosely bound water. Raisin and chewy chocolate bar. We just say chewy snack bar, chewy bar. What type of the food is the majority of them are free water? Meat and produce. Okay, therefore, we have a second question for you. What do you think is the moisture amount? Chips, low, not much water. Meat and fresh produce, lots of moisture there. We say it's high. How about the raisin and the chewy bar? Intermediate. Let's look at the texture. What do you think of the chips? It's dry, is that right? Dry. Crispy. Crispy. What do you think of the raisin and the chewy chocolate bar, snack bar? We say usually it's obviously we say it's chewy, moisty, not really moisture, moisty. How about meat and produce? It's juicy. It is juicy and soft. Okay. Then we're going to talk about shelf life. Shelf life. Because this is what we really interesting in the photochemistry standpoint. What do you think of the chips, the shelf life? It's very long. How about meat and the produce? Relatively short. Or sometimes we say it's very short. You can't just put it in the room temperature for a very long time. How about the raisin, chewy bar? Intermediate. Now, why we want to have this curve? This is a major outline of this class. Because we will talk about all the important chemical reaction related to the food quality in this class. Okay, for chips, what do we care about? Did you ever heard about Listeria monocytogenes outbreaks in chips? Never. Because it's dry. The bacteria are not going to grow. But what we care about chips? If you have a bag of chips, then you open, put on the room temperature about 3 weeks. Then you eat it, it will soft. And you see the flavor will be a little bit sweet. This is called a flavor refresher. What we care? Because at this range, this is the curve for lipids oxidation. We also gave them a name, rancidity. Flavor reversion is one of that. So, That's what we're going to talk about, the major points when we go lipids section, lipids oxidation. Raising chewy chocolate ball, what we care. Chocolate ball, we see a brownish color, beautiful brownish color. Why do we become a beautiful brownish color? Because there is a browning happens, which is called non-enzymatic browning. What is the other name for this? Maillard reaction. That's the second section. Okay. Okay, last section, what we care about. Obviously, we care a little bit about the enzyme activity, because the enzyme activity will be increased with the increase of the water activity and also the moisture content. But more we care about here is what? Foodborne pathogen. So that's my other classes talk about. General microbiology, we talk about that. And Dr. J's food microbiology talk about the foodborne pathogens. So this is not fit this category. In the food chemistry, we will talk about lipids oxidation and the Maillard reaction, the second curve. Okay, so that's the outline of what we have this way. And I will, because the space is limited, we will be repeat this curve at the beginning of next week. Then we go talk about the water activity and the moisture content, the relationship, which is sorption isosomes and absorption, desorption, and several mathematical models. Then we end up this water and then we move to the ice. Okay, so that's all we have.